Good morning. My group and I would like to present on the topic of organometallic compound synthesis. For this presentation, we have selected an article titled Synthesis and Applications of Ferrokin-Fused Nitrogen Heterocycles. We'll be explaining three different syntheses that were described in the article. We will start with the introduction to the general structure. The structure shows a ferrocene unit where one ring is fused to a pyridine ring. The image highlights three key features. First is ferrocene backbone. The molecule has planar chirality due to ferrocene backbone, meaning its lack of symmetry in a flat plane makes it chiral, useful for asymmetry catalysis. The second one is pyridine. The nitrogen atom in the pyridine provides a nucleophilic or basic site which is really important in many catalytic reactions. Lastly is the R group. The R groups on the ferrocene rings can be tuned to control steric hindrance, affecting how the molecule interacts with substrates. The first synthesis is synthesis of enantiopure ferrocene base and HC precursors. The image shows the overall view of this synthesis. Let's start with the starting material. The starting material is racemic chloro-substituted ferrocene fused pyridine, which is readily available on multigram scale. The first step is pyridine catalyzed aminocarbonylation. The racemic compound is converted into a pseudo-pyridine amides. This will yield a diastereomeric amides, and these diastereomers are separable by column chromatography. The next step is reduction with dibyl H, which reduces the amide to produce enantiopure aldehyde. The last step is annulation reaction, which involves aniline and formaldehyde. In this step, ferrocene-based azolium salt is formed. These are the precursors of chiral and heterocyclic carbene ligands. Overall, this scheme outlines an efficient route to enantiopure ferrocene-based NHC precursors through selective functionalization and annulation steps, enabling application in asymmetric catalysis.
Let's look at scheme 2, which outlines the synthesis. The process starts with iron to chloride, FeCl2. In the first step, FeCl2 reacts with the substitute cyclopentadienyl lithium reagent, denoted as C5R5Li. Here R can be a methyl or phenyl group. In the second step, the intermediate is treated with a 4-substitute pyridine-fused cyclopentadienyl lithium reagent, shown on the left of the scheme. This sequence forms a racemic mixture of planar chiral ferroxene fused pyridine complex labeled as compound 1. The racemic mixture is then separated by chiral high-performance liquid chromatography or chiral HPLC. These resolutions that give a single national product, which are essential for asymmetrical catalysis. At the bottom of the scheme, you can see some representative examples. First one, laboratory 1A and laboratory 1B, where R is a methyl of phenyl and the Y group is a dimethyl amino subsequent. Second, laboratory 1C and laboratory 1D with a different pyridine substitution. And lastly, laboratory 1E, which has multiple methyl group on the ferrocene ring. This structure highlights the versatility of the method, allowing for different substitution and functionalities. This synthesis provides access to a range of planar chiral fused pyridine. The method is modular and efficient, enabling the preparation of enantiomerically pure catalysis for asymmetrical synthesis.
For synthesized planar chiral-qualenine-fused ferrocene derivative, they start with S2 iodine ferrocene carboaldehyde, an enantiopure compound made from ferrocene carboaldehyde using canning method, which gives us the chiral purity needed for the synthesis. First, aldehyde group was reduced to a primary alcohol using a mild reducing agent like sodium borohydride. This makes the molecule more reactive for the next step. Second, a Suzuki coupling reaction was performed. Here the iodine atom and on the ferrocene was replaced with a 2-ammoniaryl group using 2-ammoniaryboronic acid or its pinnacle ester. This step creates a key intermediate that contains both an amino group and the alcohol group nearby. Finally, they use an oxidative silicization to form a new ring, a quinoline ring, which is fused into the ferrocene. This step closes the ring structure and maintains the original planar chirality. The result is a chirality quinoline fused ferrocene derivative, obtained the moderate yield but with a high enantiomeric purity, making it valuable synthesis method for the chiral ligand and drug development.